All right, so I'm going to round off our discussion about metabolic acidosis, and I just kind of wanted to start from this summary slide again as our framework of just really understanding acid-base chemistry and kind of what to do and how to navigate problems. So, just as a recap, if we have identified an acidosis, by definition, a decrease in the pH, we next look at the bicarb. If we have a reduction in the bicarb, we know we're in a metabolic acidosis state. The next thing is you can either check to see if there's an appropriate CO2 compensation by using Winter's formula. That really has nothing to do with the anion gap versus normal gap acidosis at all. Okay, so that's just the Winter's formula is only assessing of whether or not we have an appropriate CO2 change, or it's assessing whether or not we have a concomitant respiratory only problem. Okay. After you've identified if we're in an increased anion gap or a normal anion gap, then you follow different steps. But again, that has nothing to do with Winter's formula. You can apply Winter's formula to both conditions. Doesn't matter. It does not tell us anything about um, the source of the acidosis. Okay, so in order to figure out what type of acidosis we have, that's the whole purpose of calculating the anion gap, because normal gap or non-anion gap has one set of diagnostic criteria or one specific set of causes, whereas an increase in gap has a totally different set of causes. So that's the point of calculating the gap. After you calculate the gap, let's say you've identified the gap, the purpose of the delta delta is to tell us, is there something else going on to change the bicarb? What does that mean? By definition, changes in bicarb, if it's reduced, it's metabolic acidosis. If it's increased, it's metabolic alkalosis. So again, the delta delta tells us specifically only about other metabolic disturbances that are happening. Nothing to do with respiratory, nothing to do with CO2, zero. All it's telling us is if we have a concomitant metabolic alkalosis or a concomitant metabolic acidosis at play in addition to the increase in anion gap metabolic acidosis. So I just wanted to show this summary slide of kind of how to navigate this, because it gets a little bit murky when we're talking about metabolic acidosis and what the heck's the Winter's formula and what do I do next? What are the steps? But again, I think just follow the simple basic format of identifying there's a decrease in bicarb. Who cares about Winter's formula? Let's calculate the anion gap. If there's an increase in anion gap only, that's only when the delta delta formula applies. We've already been through the understanding about what that means. Okay. Last thing is that if you expect a toxic alcohol ingestion, that's when you would calculate an Osmol gap. All right. And again, I highlighted here in green um, that you could apply Winter's formula really at any time to both normal gap and anion gap. It just doesn't matter. And that's the point that I wanted to make here. Um, okay, so let's just briefly talk about this. I really love this algorithm. Um, I think it's beautifully done, and I recommend following it. So again, just what I said: decrease in bicarb, metabolic acidosis, Winter's formula doesn't matter. All it's telling us is respiratory compensation. That's it. Next thing we want to do is calculate the gap. If we've identified a decrease in gap, we would suspect things like diarrhea or um, an abundance of saline. But if we're suspecting that something else is going on, that's when we can utilize the urine anion gap. And really, what that tells us is if there is a positive gap by using this formula over here, that tells us that there is an RTA or renotubular acidosis going on, because normally the gap should be negative, right? Negative. All right. if we've identified an increase in an anion gap, we have the mnemonic of mud piles or cat mud piles, whatever. Um, so don't forget things like carbon monoxide and cyanide can also lead to these increasing gap, and then something called toluene, which is in paint thinners. So that's something I did not know. Um, and again, um, we've calculated the anion gap. We've identified the anion gap. Now we want to know if there's something else going on. So that's when we apply the lovely delta delta here. And I just think it helps to understand the concept that we've already explained, that the change from baseline should equal each other given the electroneutrality principles. So if the change is, let's just say normal, right? So 1 to 2, um, you really are suspecting either renal failure, so uremia, or a lactic acidosis, or DKA. Those are really the three that you want to identify um, in this section right here. So this means increase in anion gap with a normal delta delta. Um, we're really suspecting one of those three things. Of course, you want to check your beta hydroxybutyrate and a urine ketone, and then also, of course, checking kidney function and a lactate level. And this really determines kind of where you go from there. Okay. So just depending on the patient, depending on the given scenario, if you expect a toxic alcohol ingestion, that's when you would calculate your osmol gap down here. And again, a similar concept to the anion gap. It's just saying that there's something else in the blood that's taking up space and it's not calculated by the laboratory. And so the laboratory is picking up an increase in osmol gap, and that's not due to things like sodium or glucose or what have you. It's due to another substance taking up space and adding to the osmoles. So that's why we utilize a calculated osmol gap instead of the uh, detected or observed osmol gap. All right, and that pretty much sums it up.